Tonight, we set our sights on a world that has captured human imagination for centuries. The mysterious and hauntingly beautiful planet Mars. From afar, it glows red in our night sky, a distant neighbor that feels both familiar and completely unknown. But beneath that dusty surface lies a story that stretches back billions of years. A story of flowing water, shifting climates, and the lingering possibility that life may have once taken hold, or may still be waiting, hidden from view. As we drift through this journey, you may begin to see Mars not as a barren world, but as a place filled with unanswered questions. A planet that may once have resembled our own, and may yet hold secrets that could change how we understand life itself. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is settle in. Let your shoulders soften. Let your breathing slow. And allow your mind to drift across the surface of another world as we explore the hidden story of life on Mars together. Let's begin. Mars may once have had everything life needed to begin. There was a time when Mars was not the frozen desert we see today. Its skies were thicker, its volcanoes were active, and water moved across the surface in rivers, lakes, and perhaps even seas. That matters because life, as far as we understand it, needs more than water alone. It needs useful chemistry, energy, and stable places where tiny reactions can repeat long enough to become something greater. Early Mars may have offered all of those at once. Rock, heat, carbon compounds, minerals, and liquid water were gathered together on a young planet still changing from the inside out. It is astonishing to imagine that while Earth was becoming habitable, Mars may have been running its own experiment in biology. Somewhere in that ancient world, in mud, stone, or warm underground water, chemistry may have taken its first trembling step toward life. Ancient Mars was wetter, warmer, and far more Earth-like than today. Look at Mars now, and it feels almost impossible. The air is thin, the cold is extreme, and the surface is dry enough to make Earth's harshest deserts seem generous. Yet the landscape tells another story. Spacecraft have photographed dry river channels, fan-shaped deltas, rounded pebbles, and minerals that usually form in water. These are not small hints. They are the remains of a planet that once behaved very differently. Rain or snow may have fed streams. Lakes may have lasted long enough for sediment to settle in layers. The surface may have had seasons, shorelines, and water moving through soil. This does not mean Mars was ever a twin of Earth, but it may once have been close enough to feel strangely familiar. The most haunting part is that this warmer world did not vanish completely. Its memory is still written into the ground. A dried Martian lake may hold clues to vanished microbial worlds. Jezero Crater is one of the most important places humans have ever studied from afar. Billions of years ago, water flowed into this basin and spread into a lake. At its edge, a river built a delta, dropping mud, sand, and minerals in layered deposits. On Earth, deltas are excellent places to preserve traces of life because they gather material gently and bury it quickly. That is why this Martian crater feels so powerful to scientists. It is not just a hole in the ground. It is an old water system with a record of changing conditions, carried forward in stone. If microbes ever lived in that lake or along its muddy edges, tiny chemical or structural traces might remain sealed inside the sediments. The landscape is silent now, but its rocks may still hold evidence from a time when Mars had standing water under an open sky. NASA found organic molecules in rocks from ancient Martian water. Organic molecules are important because they contain carbon, one of the central ingredients in known biology. They are not proof of life, because they can form through non-living processes as well. Still, finding them on Mars is deeply intriguing. Some were detected in ancient mudstone which formed when fine sediment settled in water long ago. That means delicate carbon chemistry survived inside rocks that once belonged to a habitable environment. Think about what that implies. Mars did not simply have dry dust and rusty stone. It had places where water, minerals, and complex chemistry met together and were preserved for billions of years. On Earth, those are exactly the kinds of settings where life leaves subtle traces. The discovery does not answer the great question, but it sharpens it beautifully. Mars had some of the right ingredients in some of the right places, and the search became far more serious. The rover named Perseverance collected a sample that may contain a possible biosignature. One of the most exciting discoveries from the rover's journey came from a rock nicknamed Chayava Falls. It contains unusual features that scientists found worth preserving for future study. The sample includes organic compounds, mineral patterns, and tiny spots associated with chemical reactions that, on Earth, can sometimes involve microbial life. That detail matters. It does not mean life was present. Nature can produce surprisingly similar patterns without biology, especially in ancient rocks shaped by water and chemistry. But this is exactly why the sample is so valuable. A rover can study Mars with remarkable instruments, but laboratories on Earth can examine tiny details with far greater precision. If that core ever returns here, scientists could test it with tools too large and delicate to send across space. The wonder is not that we already know what it means. The wonder is that Mars has handed us a question so specific, so strange, and so worth answering. Martian life, if it survives today, may be hiding underground. The surface of modern Mars is a difficult place for biology. Radiation reaches the ground more easily than it does on Earth. The air is thin, liquid water is unstable, and temperatures swing sharply between day and night. But underground, conditions could be different. Soil and rock can block radiation. Temperatures may be steadier. Ice may be protected from sunlight, and pockets of salty moisture might occasionally appear in hidden spaces. On Earth, vast communities of microbes live deep below the surface, far from daylight, using chemical energy from rocks and water. That earthly example opens the imagination. If life ever began on Mars, it may not have needed to disappear when the surface changed. It may have retreated downward, following water into cracks, pores, and buried habitats. The most important Martians, if any exist, may never have seen the sky. Mars lost most of its air, and its surface became hostile. The story of Mars is partly a story of escape. Long ago, the planet had a thicker atmosphere that helped shape a more forgiving surface. Over time, much of that air was stripped away into space. Mars is smaller than Earth, and its gravity is weaker. It also lost its global magnetic shield, which left the upper atmosphere more exposed to the solar wind. As the air thinned, pressure dropped. Water became harder to keep stable, and the planet cooled into the dry world we know now. This transformation is one reason Mars feels so tragic and fascinating. It may not have begun as a barren world. it may have slowly turned into one. A planet that once had moving water and richer possibilities was slowly altered by physics on a global scale. The search for life there is also a search through the ruins of a lost atmosphere. The red planet still keeps huge reserves of buried water ice. Mars may look dry, but it is not empty of water. Ice lies in the polar caps, beneath the ground, and across parts of the middle latitudes. Some of it is close enough to the surface that future explorers may be able to reach it. That ice is more than a survival resource. It is a scientific treasure. Frozen water can preserve climate history layer by layer, much like ice sheets on Earth store records of ancient air and dust. It may also protect organic chemistry from some of the harsh conditions at the surface. For future astronauts, buried ice could become drinking water, oxygen, and rocket fuel. For scientists, it may reveal how Mars changed from a wetter planet into a frozen desert. The same hidden ice that could help humans live there may also help explain whether anything ever lived there before us. Tiny fossils on Mars would change humanity's place in the universe. A discovery would not need to be large to be revolutionary. It might be a microscopic structure inside ancient rock, a chemical pattern left by cells, or a mineral texture that only living communities are known to make. The size would not matter. The meaning would be enormous. If scientists found convincing evidence that life once existed on Mars, it would show that biology is not a one-time miracle restricted to Earth. It would mean life appeared on two neighboring planets in the same solar system. That would suggest the universe may be far more fertile than we have dared to assume. Even extinct microbes would change the story. They would make Mars not just a planet of geology and weather, but a second chapter in the history of life. A tiny fossil could become one of the largest discoveries ever made. Future astronauts may search for life beneath Martian dust. Robots have transformed our understanding of Mars, but human explorers would bring a different kind of ability. They could choose samples quickly, notice unexpected details, drill with flexible judgment, and adapt when a landscape surprises them. The most promising searches may happen below the surface, where ancient materials are shielded from radiation and weathering. Astrolabes might examine buried ice, crack open layered rocks, or enter lava tubes where time has left things more protected. This would not be casual exploration. It would require careful suits, sealed tools, clean procedures, and deep respect for contamination. The goal would be to avoid carrying Earth life into the very places we hope to study. There is something breathtaking about the possibility. One day, a human hand may lift a piece of Martian stone and hold, within it, the answer to whether life ever began on another world. Jezero Crater once held a river delta rich with possibility. From orbit, this place looks like a frozen memory of moving water. A channel enters the crater, spreads into branching shapes, and leaves behind a fan of sediment that resembles river deltas on Earth. That shape is one reason the rover was sent there. Deltas are natural collectors. They gather mud, minerals, and tiny chemical fragments from wide landscapes, then bury them in layers. On Earth, those layers can preserve delicate traces for immense stretches of time. In this Martian basin, each band of rock may represent a changing shoreline, a shifting current, or a season when water carried new material into the lake. The wonder is not only that a river once flowed there. It is that the river may have delivered ingredients from beyond the crater and tucked them away in stone, creating one of the best places to read Mars's ancient story. Gale Crater preserved ancient lake mud inside layered mountain rocks. The Curiosity rover landed in a place that looks almost like a geological library. At the center rises Mount Sharp, a mountain built from stacked layers of sediment. Those layers record changes in the crater across deep time. Near the base, Curiosity found mudstone that formed when fine particles settled in calm water. That detail matters because mud can seal information very gently. It can capture chemical clues without the violence of fast floods or crashing debris. The rover also found signs that the water there was not wildly acidic or impossible for life as we know it. It may have been a fairly mild lake environment for a time. As Curiosity climbed, it moved through pages of Martian history. Lower layers spoke of lakes. Higher layers showed a world drying out. One mountain became a timeline of a planet losing its wetter youth. Mars had rivers long before Earth had complex animals. The dry channels on Mars are ancient beyond easy imagination. Many formed billions of years ago when Earth's life was still mostly microscopic and the great drama of animals, forests, and people had not begun. This gives Martian rivers a strange kind of power. They were flowing under a younger sun, across a world whose future would turn away from habitability. Their channels still cross the surface because Mars lacks Earth's active weather, oceans, and plate tectonics. On our planet, old riverbeds are often erased, buried, folded, or recycled. On Mars, they remain like abandoned writing. Some valleys twist across highlands. Others feed into basins where lakes may have formed. To look at them is to see water moving through a world that was alive with geology, at a time when Earth itself was still preparing the stage for complex life. Some Martian valleys look carved by long-vanished floods. Not every channel on Mars tells the story of a steady river. Some landscapes look as though enormous releases of water rushed through them with violent force. Wide outflow channels stretch across the surface, far larger than ordinary streams would carve. They suggest sudden floods, possibly unleashed when underground water broke free or ice was melted by heat from below. Imagine a sealed reservoir beneath frozen ground, trapped for ages, then released in a catastrophic surge. Water would tear through rock, carry boulders, carve streamlined islands, and race toward lower plains. The event may have lasted only a short time compared with the age of the planet, but its mark would remain for billions of years. These channels show that Mars was not only shaped by slow lakes and patient streams. It also knew moments of sudden release, when hidden water burst outward and rewrote the landscape. Ancient shorelines may mark where a northern ocean once spread. One of the boldest ideas about early Mars is that a great ocean may have covered much of its northern lowlands. The evidence is debated, but it is fascinating. Some researchers have traced possible shoreline features around the planet, as if water once stood at a common level across a huge basin. If that interpretation is right, Mars was not merely a world of scattered ponds and temporary streams. It may have held a body of water so large that it shaped climate, weather, and chemistry on a planetary scale. The northern plains are lower than the southern highlands, so they form a natural place for water to collect. A Martian ocean would have changed everything. Waves could have worked the edges. Sediments could have gathered along its floor. Even if the ocean was icy, temporary, or uneven, the possibility gives Mars a lost geography almost impossible to ignore. Mars still has minerals that only form in lasting water. Rovers and orbiters have found minerals that are difficult to explain without sustained contact with liquid water. Some of these minerals form when volcanic rock is altered over time. Others appear in deposits left behind as water evaporates. They are like chemical footprints, each one pointing to a different environment. Certain salts suggest drying basins. Some hydrated minerals show that water became part of their crystal structure. These discoveries matter because water that lingers can change rock in deep and revealing ways. A brief splash leaves less behind than a lake, spring, or groundwater system. By mapping these minerals from orbit, scientists can trace where water once pooled, flowed, soaked, or vanished. Mars does not need to tell its story in words. Its stones have been altered by contact, and that alteration is a language. Every hydrated mineral is a small confession from the planet's wetter past. Clay minerals can protect fragile organic molecules for billions of years. Clays are some of the most valuable materials in the search for ancient life. They form when water changes rock, often under conditions that can be relatively mild. Their tiny layered structures can trap and shield molecules that might otherwise break apart. On Earth, clays are excellent at preserving traces of past environments because they can hold chemical information inside microscopic spaces. On Mars, this makes clay-rich regions especially tempting. If carbon-based compounds settled into mud at the bottom of an old lake, clay minerals could have helped protect them from later damage. They cannot stop time completely, but they can slow destruction and improve the chance that something meaningful remains. This is why scientists care so deeply about fine-grained sediments. A plain piece of Martian mudstone may not look dramatic, yet it could be one of the safest vaults for ancient chemistry. Sulfur on Mars could have fed ancient microbial chemistry. Life does not always need sunlight. On Earth, many microbes use chemical reactions for energy, and sulfur can play a powerful role in those reactions. Mars has many sulfur-bearing minerals, and they point to a planet with active chemical environments. In some ancient settings, sulfur compounds may have moved through water, reacted with rock, and created energy gradients that microbes could exploit. This does not mean anything was alive there, but it means the fuel options were more varied than simple sunlight at the surface. Sulfur chemistry is especially interesting because it can operate in places where light is weak or absent, such as underground water systems. If Mars ever had microbes tucked beneath its surface, they might have relied on chemical exchanges rather than photosynthesis. The red planet's mineral record hints at a world where energy could have been hidden inside the rocks themselves. Iron minerals may record energy sources once useful to microbes. Mars is famous for its rusty color, and iron is part of that story. But iron is more than a pigment. It can change form through chemical reactions, gaining or losing electrons. On Earth, some microbes use those reactions as part of their metabolism. They do not eat iron in the ordinary sense, but they draw energy from transformations involving iron compounds. Mars has abundant iron minerals, and ancient water could have created places where different iron forms met and reacted. Such zones would have been scientifically exciting because they offer both a record of environmental change and a possible energy source. Iron can also leave visible signatures in rocks, including veins, concretions, and color bands. These features may tell scientists where fluids moved and how chemistry shifted. In a search for life, even a rusty stone can become a clue to once active environments. Carbon compounds on Mars are not proof of life.